250 million years ago, the beginning of the Triassic period is marked by the extinction of 83% of all genera, known as the Permian extinction. With unrelenting conditions such as high volcanic activity, a stifling atmosphere with dust clouds and high CO2 levels, there's a reason it earned the nickname the Great Dying. Temperatures were 18 to 54 degrees higher than they are today, with black oceans averaging 104 degrees.
Of the few that survived, reptilian therapsids, called listosaurs, dominated the land. It took 10 million years of recovery to start restoration of biodiversity, and 30 million to be fully restored. More toward the end of the Triassic, however, the listosaurs were outnumbered and pushed to extinction by a large, more diverse group of therapsids, the ancestors of all mammals, called cynodonts. Shortly thereafter, the cynodonts were forced into nocturnal existence by what became dinosaurs, and finally our birds and crocodiles of the present, the Archosaur group.
But what made them so much more successful? Archosaurs likely had lungs more like birds do today, making it easier to breathe in the harsh conditions of the early Triassic. In the mid-Triassic, the Archosaur group diverged into crocodilians and proto-bird theropods, sporting the earliest form of feathers, perhaps similar to down. It should be noted that the closest living relative to the T-Rex is the chicken.
It is theorized that thermoregulation came about as a result of parental care. Despite its obvious disadvantages of endothermy, such as need for more food, a higher body temperature is correlated to higher aerobic capacity, which is related to the relative stamina of an organism, also associated with the presence of respiratory turbinates found in present-day mammals, some birds, as well as their ancestors. Recalling the unrelenting atmospheric conditions of the early Triassic, it should be apparent why it would be beneficial to be better adept at breathing. Higher body temperature also allows for direct parental care, protection of young, and incubation of eggs that ensures survival of young, conveying higher fitness to the population, as well as niche expansion. The tegu lizard is a living example that supports the parental care theory of the origin of endothermy. Incredibly, during the reproductive season, the tegu lizard, who is approximately the size of the earliest mammals, is able to increase their metabolic rate and produce heat internally the way that mammals and birds do. As we can see, there's not only one way to be warm or cold-blooded. An endotherm, like this tufted titmouse, is an individual that has the ability to control their internal body temperature by increasing their metabolism.
Ectotherms are individuals that rely on external sources of heat, as internal sources are negligible. These, like snakes and lizards, are the animals that are generally referred to as cold-blooded. Homeotherms maintain a stable internal body temperature regardless of external conditions. Alligators, for example, are ectotherms, however they are homeothermic, maintaining a stable body temperature through the night.
The internal body temperature of a poikilothermic individual fluctuates greatly. These include types of vertebrate animals such as fish, amphibians, and reptiles. The naked mole rat is currently the only mammal that is thought to be poikilothermic. A heterotherm is an animal that switches between poikilothermy when at rest and homeothermy when active, such as the tiny hummingbird, who slows her heart rate from over 1,000 beats per minute down to 40 beats per minute, lowering her body temperature from her daily average of 104 degrees Fahrenheit to 70 degrees Fahrenheit every night in a state called torpor.
Evolution of endothermy gave our ancestors the stamina and ability to survive harsh living conditions and therefore occupy more niches. We've come a long way from being scaly, ground-crawling, plant-eating, reptile-like mammals. We can no longer consider organisms as merely warm or cold-blooded. The variations are more akin to points along a spectrum between endothermy and ectothermy. The diversity of thermoregulation around the Earth makes it impossible to neatly divide species into such strict classifications.